Okay, my friends, this is my explanation of Don Lincoln and Fermilab and CERN and all of them, their particles, and what we found. Now, again, this is part of the book, and I am going to refer in and out of all of these different videos that I did in response to this, which I've never had a single response to my videos from people like Don Lincoln, who refuses to engage. However, I found the exact same particles he was looking for, and he claims they do exactly what I claim they do. There's a fixed particle and a point particle. Now, this is from 2013. We're going to go on to his explanation of the quantum foam, because this all fills into the quantum foam, too. And this was actually the same time frame, 2013. Now, so in summary, he says extended particles, which was that black one, have a fixed size. They may have a fuzzy edge, which they do. The point-like particles are mathematical abstractions with zero size. That is possible. I can't dispute that. And I can't dispute the fixed size either. He was right about the things he was saying. This is what astounds me. He won't interact with me. I found exactly the particles he's looking for. Absolutely amazing. Anyway, but even zero-size particles have an extended field. Yes, everything has a field around it. Anything that is anything has a field. So I can't see where it has a zero size, but I can see where it may have almost no size at all. But there must be something to support a field, I would think, but that's just my estimation. Now, again, look at these particles. The point particle is fixed. This one is the glowy little bugger. Okay, so you saw Fermilab's fixed particle. There it is right there. And their point particle, there it is right there. These can get bigger and smaller, and they glow like hell, and they are hot. These are cold and slammers and never change size. This is what a photon is, and that is the fields and the energetic values of this photon, same photon. This is leading going this way, so this one is charging up as it concusses with these little bitty particles that are in front of it. If you can see those little bitty particles there. I'm sorry, let me get in there a little closer, see how? I don't know if you can or not. Yeah, there you go. I think you can see them now. They're hard to pick up sometimes, but I have other shots that show a total interaction between the light and the particles that are in the air. Now, what else did we do with this particle? We accelerated it. We accelerated that light, and that's how we were able to see these. And then at the end of the acceleration at the Venturi, which is what forced it to accelerate, it exploded, and the black came away from the white. So we had a muon and an electron neutrino, the black and the white, there they are right there, muon, electron neutrino, muon, electron neutrino. Two of them back to back make a photon. One of these alone, just one black and one white, is an electron. That's what we always thought was just a glowy little burny particle. It's not. It's a black and a white. Now, here they concussed and separated. So we have created what Don Lincoln has been looking for, that muon electron shower. And this is it's not, I'm not making anything up here whatsoever. This is light from a pulsed red laser. This is its energetic values, which CERN and Fermilab have seen and have documented, and they say it's fixed, and this is squishing. I absolutely agree. No question whatsoever, I agree. And the title of this video from 7 years ago was Light is Dark Energy and Matter in the Vacuum of Space. There is no vacuum, and that's what Don Lincoln says too. He says it's a quantum foam. It's filled with these particles. Not only that, it's filled with dust and everything else. Now here's Don Lincoln again, 2013, quantum foam. Empty space isn't empty. Correct. It's filled with these particles. It says the quantum foam is real. The microcosm is in continual motion. The universe is not only stranger than we imagine, it's stranger than we can imagine. And he can't even imagine how strange that will be. But he says empty space isn't empty. That's correct. It's a quantum foam. It's particles blinking in and out. We're going to watch his video on this, and I'm going to explain what he's missing. And again, this goes back to 2013. That's 9 years ago. And I have been trying to push this, and my work was done 2015. I had everything done that we had to do, and it's still, he won't look at it. That's my problem. And this is what causes me my real annoyance with science. Science, oh, follow science. Well, if you don't look for the science, what are you going to follow? All you're going to do is listen to what you're being told. And that's how Don Lincoln handles science. Okay, let's get into full disclosure, because I've had a little bit of a discord with Don Lincoln and Fermilab, and really all the other physicists, because they refuse to engage, call me all kinds of names and so forth. This goes back to October 2014, and we had a phone that was from 2012, a Galaxy S3, that could see these same as, much like the high-end multi-million-dollar observatories. It made them go insane when we said we could see these particles, and we could. It says the smartphone could harness to detect cosmic rays. Well, what is cosmic rays? It uses the same principle as the very large experiments. Well, cosmic rays are muons, right? Cosmic rays are energetic subatomic particles. And the scientists think they come from black holes and so forth, exploding stars. Well, we can make them by forcing the fields together, causing the Casimir effect to crush the fields instead of hitting head on. All right, so the particles crash into Earth's atmosphere. They create secondary particles called muons. So the muons are cosmic rays. And that's exactly what we're seeing is the muons. So this is what drove them crazy, because we had all the equipment right on my desktop to do exactly what they were doing at CERN and Fermilab, only they weren't doing it. They weren't doing their job. They missed everything because they tried to start with protons instead of photons. They tried to use the photons. Nobody ever could figure it out. And I'll show you that too. Again, this is all to back up the book. The book hopefully will be coming out soon. I've got a whole plethora of things to cover, which is failure in science. Now, let's just finish up with the smartphone. Here's why we're getting such extremely elegant pictures. We're taking pictures right at the source of the radiance. We're not picking them up away, from outer space. Smartphone cameras use silicon chips that work through what is called photoelectric effect, in which particles of light, which are these muons, or photons, hit a silicon surface and release an electric charge. The harder it hits, the more energy, the brighter the charge. The same is true for muons. They do the same thing. When a muon strikes a semiconductor that underpins the smartphone camera, it liberates an electric charge, creates a signature in pixels that can be logged, stored, and analyzed, and that's precisely what we did. Now here's another bit of research being done at the exact same time. See 2P, 2H, that's two particles, two holes. They saw these particles apparently. I didn't really get too deep into their research, but what I did come across was that it appears that they're talking about neutrinos in the nucleus, yes, which is the muon and the electron neutrino. They're quasi-elastic, yes. They wobble and spin and all that stuff, no question. They have two particles and two holes. You could take it that way, yes, absolutely. And over a certain gigavolt range, I believe this is the way I'm interpreting their research, they detected an increase in energy. And it might have been even by 14%. I don't know. I really don't know. I can't forget this. I forget. This is 9 years ago. This is the same time frame, and the same time frame we're doing our work. And we had the answers at this point. So let's see what Don Lincoln has to say about quantum foam, which is my particles that are in space, which are light. All right, these are all the things that CERN was hoping to do and never could see, because they're working with huge particles and smashing them to bits. And they're using the same effect, which is the Casimir effect, but only they're hitting head on. So they can swing off this way, and they really don't get them good smacking. We force them into each other's fields, crush them, literally crush them. That's why we have such exquisite results. This is the light particles coming through the air, interfering with the little particles that are in the air, which are electrons that are attached to other molecules in the air, which is heat particles and so forth. Now, this is, and everything there is coated with electrons. That's why we've never seen inside. The dark matter literally is inside. We never saw it. It is a carrier. It carries the white particles on the outside of it. Once you get beyond the photon range. So here, let me just show you something. I'm going to show you something that hopefully you'll understand. An electron is made of two particles. One of them is the black one of them is the glowy white one that can get smaller and bigger. This one is a hammer. All right, we're going to talk about that hammer in a second. This one is just a little squirter, almost just like water. All right, and they are coming through together, but they are in a 4-pack, like this. This is exactly what a particle, there are 2 black ones and 2 white ones. And they come this way. They don't spin this way, they spin this way. All right, as the one in front charges up because of bumping into these particles, it will swell up and then it'll flip to the back. And then this one will start to charge up. We have seen this, and I will show it to you right now. So this is light from the pulse red laser. It wouldn't even be this bright, except it's getting ready to start seeking the Venturi. And here is the Venturi that it is seeking. We were looking right here, is about right up in here somewhere, just before it starts to liberate the particles. All right, which particles are light particles. I just showed you what they look like, and you'll see them again vividly. This is the stream of particles. It is exceeding the speed of light, and it's pulled itself out of its light wave, because light is a particle. Remember, don't forget, it's the particle, but it creates that big wave in front of it because it's magnetic. It has a magnetic field around it. That's all it is. It's a wave-particle duality. As simple as that. Very, very simple when you stop and think about it. Now here, we have a concussion that caused the division of the black from the white. We saw they were attached together right here. You see them there? That's what they look like as they are approaching the Venturi. Just like I showed you with my little, it's just a low budget operation. Anyway, it comes through here, and when they hit the Venturi, I'm sorry, I can't help myself. It is low budget. You can't even imagine. All right, so here comes the particle. Pow! Well, what happens? They want to see Higgs fields, they want to see sterile neutrinos, they want to see electron neutrino showers. Well, we got them. Here's the Higgs fields. Between here, the outlet of the Venturi, these are electron showers, and then they turn into the Higgs fields. Let me show you what CERN says, and in Fermilab, I'll show you exactly what they say. Alright, so my theory is that everything is dipoles, and everything is made of muons and electron neutrinos, and they start out with the only smallest particle really is an electron, but it has these 2 parts. Nobody's ever seen a dark part. Now we get to photons, which are nothing more than 2 of these back-to-back like bar magnets. They have a mass. Each one of these electrons weighs about 0.000545 atomic mass units, because one proton, which is the big ball, weighs 1 atomic mass units, and there's 1836 or so in that proton, 1835. Now we get to the photons, and we still have 2 dipole particles. My theory from 1970 was dipole-dipole interactions only, and that light was an atomic vapor. You see this? Transfer of energy from light is to atomic vapor. 2 types of interactions, dipole-dipole interactions, that's it. You have to have centers and, anyway, it got very, very deep. And I mean, I did a lot of this. I didn't just do one thing. I did all the chemistry, I did thermochemistry, I did everything. I did it all. Everything there was to do with material science, I did. So I will speak with anybody about this. And this goes back 50 years ago, and I never stopped. Now, let's see about these energies. Visible light, look at this, only takes 1.5 to 3.5 electron volts. That's visible light. We're using lasers. So let's say we're way up here and we're in the gamma radiation, which is about 3 million electron volts. Let's say that's how much we're using to create the laser light. And that's high on the upper end, trust me. 3 million. Well, guess what? If we can create cosmic rays, we're in the 1,000 trillion electron volts. And you saw them. They were cosmic rays, which are muons. So what is it we have here? Let's just look at the whole ball of wax, and then we're going to look at what Don Lincoln has to say. This is what we would call a photon. Remember I said they're back to back? And then they don't glow much when they're not being really excited. But now, all of a sudden, this one's getting excited. The red ones they're blowing up because they're smashing into things very, very hard. So now that's a photon excited. This is a normal photon, just sort of working its way around. Now, then, at the Venturi, which is this, all the fields have to crush. That's what's called a Casimir effect. Casimir. Now, what Fermilab's doing, they're hitting things head on this way, bam, bam, head to head. Same effect. They're hitting fields against fields, but they shoot off this way and this way. They get very, very poor results. We're forcing the big black heavy-duty fixed particles to work as a jackhammer to squirt the white particles right out of here. And they squirt out of there like you saw them squirting. This is what's called fission. When the black comes away from the white, that's fission. It's fission. It's atomic, subatomic fission. Now, what happens here? The white is all by itself. We saw that, and I will show it to you again many times. And immediately the black ones start to come back in, if they can, around the edges. But here, it's so excited, they say, stay out of here, everybody get out. And then all of a sudden, shoo, right here, the blacks start pulling back in, and then you have the Higgs fields. So this is fission, this is fusion right here, and then the Higgs fields start right here. Down here, we're in the 1 mega electron volts, somewhere around. Let's just go with that. Up here, we're in the trillion electron volts. That's what's called increase of energy, exponentially. I say if we can put some harvest device right in here, right down that line, before it hits here, and suck all that energy back, and then feed it back to the black ones, use all that energy to drive a car, a plane, heat your house, lighting, and you could carry it around in a little box. And I have a box right here. This is how powerful this would be. I say, and I want somebody to say I'm wrong, I say something this size with a bunch of arrays of receiving chips, and these are just nothing more than lasers, really high-powered lasers, and Venturis. I mean, we're talking this small. You could have thousands of them in a box like this. And what would it do? It would create enough electricity, I say, to power a house, your cabin in the woods, carry it out in the woods to fight fires, electricity, pump water, create lighting, drive boats and cars and planes and anything you want. No grid required, but you certainly could put it on the grid, absolutely. Everybody still wants to stay on the grid, I would assume. I don't want to have to come in here and plug it. Well, if I just plug my house into that, I'd be okay. But I'd want to still be well, who knows? This is a whole new world. Whole new world. And if this is all we have to do, everything is on the shelf right now. I've shown this a million bazillion times. Had very little interest, but I'm telling you right now, all I hear is about, we need energy, we're ruining the earth, not a single person will pay attention to me. And I am showing you something that cannot be denied. It has to be examined, then they can deny it. But they can't deny it out of hand. And that's what's happened. And that's Fermilab, CERN, all of them. And I was upset. I went to, they wouldn't talk to me, so I ended up going to University of Geneva, online, for particle physics, and I told them exactly what I was doing. I was focusing the particles and through the Venturi, and we were creating all this stuff, and I started with light. I'm not using protons. I went through the whole thing. They listened, and they said, wow, that's pretty amazing. We'll follow you. And I said, you kidding me? Why don't you do this? And I never heard back from them, but then about a year later, I think, or so, they shut down CERN to make it focus. Before, they were just passing them around, hoping something would hit each other. Then they focus them down so that they're hitting head on, and now they're finding all kinds of particles. They're finding the same particles I show. They call them now tetraquarks. They're coming up with all these exotic names to make it sound like they found something special. This is what they found right here, my friends. They found electron flood theory, the photons and the electrons, muons, electron neutrinos. They're finding all the same stuff, but they're still just working with debris. Debris. They're hitting them head on. The thousands of people sitting around looking at the particles saying, ooh, look at that little one, look at that little one. And then they find a whole batch of pretty small ones. They call it their particle zoo. All there is these two particles right here. Everything, take these two together. Well, first of all, you have the muon, electron, neutrino. You put them together, they call that a gluon, which means they're glued together. Yes, absolutely they are, no question whatsoever. Then they call that a photon, and they're two gluons together. Yes, absolutely no question whatsoever. And then everything is made from them. However, they have a whole different idea of it. They say, oh, then we got this one, an up spin, and a down spin, and a back spin, and an overspin, and it goes on and on and on. That's it. Case is closed. Okay, I told you the CERN just opened back up again. Now they're finding all the same particles I told them about 7 years ago. So I don't see this as any big discovery. But these physicists at CERN just made an incredible discovery, changes everything. Well, I made it 7 years ago, so good for them. Here's another one. LHCb discovers 3 new exotic particles. There is nothing that exists except the muon and electron neutrino. I'd like to see how they come up with these new particles. They're seeing a batch of particles attached together and say, ooh, look, there's 3, that must be a new particle. Ooh, look, there's 2, that must be a new particle. No, there's one of these and one of those. That ends it. Tetraquarks are nothing more than photons. They're trying to make everything, crazy, exotic. Add 3 new exotic members. Well, they keep adding things. They got to start subtracting. Okay, my friends, this should be very interesting. I am going to address all the things that Don Lincoln is going to refer to in the quantum foam. Now, I showed you the particles that he showed, which they had seen and had no clue where they came from because they're just smashing debris together. I knew the particles. I knew where they came from. I could see them develop as photons. I could see them split, which is fission and fusion. So, let's talk about, I should probably make one statement. Before,
about 100 years ago.
Okay, about 100 years ago is when they tried looking for this stuff, and nobody's ever been able to find anything. And he comes out in front of this diagram showing the Feynman diagram over here. You see it right over here. They think quantum stuff comes out of nothing. It's kicking off the muons and the electron neutrinos. These are all the things he just does not understand. Now, I did not hit it off well with Don, because he refuses to look at anything I present, and he called me a tinfoil hat guy, and it did not go well at all. I can tell you that right now. We had some harsh words, and I expect to be vindicated by doing this because he has the platform. I have no platform. I have every bit of capabilities he has, and far beyond his. No one will stick up for Don Lincoln. No one. Nobody's spoken up for him whatsoever. He won't speak up for himself. So what does that tell me? That tells me that he has no ability to do what he's doing, and he shouldn't be doing what he's doing until he acts as a scientist and engages. So I'm coming at this with a little bit of an attitude. Yes, that's the way it's going to work. I cannot go through this for 7 years having this much evidence and being denied to speak. And that is, once you get people on the top like this that will refuse you, they say, go to show Don Lincoln this stuff. I've had people say that. I've had the same thing about my other work. Show this guy, show that guy. Boy, you could roll, this is amazing. And then they won't look. So what do? This is what you do right here.
Our understanding of the fundamental governing rules of the universe.
The fundamental governing rules of the universe. Our understanding of that. Let's see what Don's understanding of that is. Now, this is from Fermilab. This goes back to 2014, same time. This was anyway, let Don have his say. and I guarantee you I will have my say.
Changed in a radical way. Rather than the simple and relatively intuitive world of pendulums and pulleys, Newton's law of gravity and Maxwell's equations of electromagnetism, the discovery of quantum mechanics and Einstein's theory of relativity showed us that, at its core, the universe behaves in rather unexpected and non-intuitive ways. We learned that moving and stationary clocks tick at different rates, and that Schrodinger's cat...
That is ridiculous. They do not tick at different rates. They're using atomic clocks, which are push to shove. They have them set to a certain frequency vibration depending upon the atomic values that that clock possesses. As they go flying through the universe, it picks up energy. That's why the thing clicks faster. Very, very small amount, because they try to insulate as much as they can, but they can't. You cannot continue through the universe in motion and not gain energy. It's as simple as that. That's all they're seeing here. So these are every one of his assumptions I am going to address. All right?
was simultaneously dead and alive.
This is kind of nonsense that they've come up with, and then they draw these huge salaries and get all these grants and everything, and we're paying for this.
These ideas, and others like them, have bothered scientists, both professional and amateur, for nearly a century. In fact, it's unusual that a week goes by when I don't receive an email or letter from some curious soul.
Yeah, some curious soul. I didn't send him a letter, but I sent him an email, along with the Russians, who were doing research in space. And they actually created a black hole in space. I'll show you that. But anyway, he gets a lot of people, because he says, ask me the questions, ask me the questions. He told me, don't ever contact me again because you're a tinfoil hat guy. And I said, I have all the stuff you're looking for. What can I do? He said, you got to get peer reviewed. I said, will you peer review me? No, I won't. So what do? They won't publish it anywhere because Don Lincoln won't look at it.
Who thinks they've found a fatal flaw in the theories of quantum mechanics and relativity.
Absolutely.
It is very rare that these communications include an idea that wasn't asked and answered years ago. The simple fact...
That's the problem. It was asked, all right, you go back and look at this, go back and look at that. No, I said, you look at what I present. I looked at what you present. I know everything that you said. I have absolutely no question what you said. I understand what your thinking is. It's wrong. You have to look or you are not a scientist.
...is that while these theories are counterintuitive for most people, they also agree remarkably well with measurements. Like it or not, they're here to stay.
No, they are not here to stay, Don. They are gone, my friend. And everyone knows this now except you.
Special relativity was developed in 1905, and it was in the 1920s in which a cadre of physicists worked out the rules of quantum mechanics. Initially, these two theories were invented independently, but if they were both true, then the two ideas needed to be blended together into a theory that is now called relativistic quantum mechanics. In 1928, British physicist Paul Dirac began that process. His equations predicted a new form of matter existed, what we now call antimatter. I talked about antimatter in another video, but the upshot is that the discovery of antimatter in 1932 by Carl Anderson gave physicists considerable reason to not only believe in quantum mechanics and relativity separately, but to also believe that Dirac had combined them properly. The 1940s brought with them a fuller understanding of the quantum realm. Physicist Richard Feynman, Julian Schwinger, and...
Let me just tell you one thing right now. Nobody understands the Feynman diagrams, not even Yale. The professor comes out, he says, nobody understands it. Feynman doesn't understand it. I don't understand it. All I can do is teach you to say what I tell you to say, and then go back and tell everybody else to say it. I'm going to show you that because I'm not kidding you. That's exactly what they say from Yale. All right, this is online. Yale has their courses online. You can go and watch. You don't get any credit for it, but you can see what they have to say. Now, listen to what he has to say.
So this is a very exciting day for me because today we're going to start quantum mechanics, and that's all we'll do till the end of the term. Now, I got bad news and good news. The bad news is that It's a subject that's kind of hard to follow intuitively. And the good news is that nobody can follow it intuitively. Richard Feynman, one of the big figures in physics, used to say no one understands quantum mechanics. So in some sense the pressure is off for you guys because I don't get it and you don't get it and Feynman doesn't get it. The point is, here's my goal. Right now, I am the only one who doesn't understand quantum mechanics. In about 7 days, all of you will be unable to understand quantum mechanics. Then you can go back and spread your ignorance everywhere else.
I don't know what to say, but that's true, because they don't really understand it at all. Feynman didn't understand the diagrams he was drawing. I understand them perfectly well, and I will show you I can understand them. All right, here's right here, LHC. This is right from CERN. As a photon collider. They wanted to do this in 1978. They had a big meeting to try to do this. They can't explain what's going on here. Here's what's happening. A proton and another proton is coming together. That's what they do, is smash them together. Well, in this case, they just happen to interact by bouncing into each other, very similar as to what we did in the Venturi, only we're using light particles. So we're starting with light. They're starting with protons. They created basically light particles, which are photons. The photons interacted with each other and created the muons and electron neutrinos, which are the bosons, W and Z bosons. That's all this is, right? Very, very simple. And they think these popped out of nowhere because they're started with gigantic particles. So these are so small that, you know, one of them has no mass and one of them has a huge mass. The white ones and the black ones. I showed you this. Now, listen to this. They're starting with 100 trillion bazillion particles, smashing them head on and accidentally hoping that they'll hit each other. Around 25 or so actually will, out of this many. Everyone we shoot in there, we're squirting them through like, anyway. Plus, they can only dig through it and find what is just debris. So anyway, look at this. The physics case for studying photon collisions. Well, photons are very hard to collide head to head, but they're not hard at all to collide in a Venturi. And that's what we did. So the physics of photon collision has been a topic of some interest for many decades. Indeed, a special meeting in 1978 to discuss how to do it, colliding electrons with positrons. Now, the collisions are very clean as we're colliding photons, which is what we did, which are elementary particles, not composite ones like protons. So exactly what we did. And that's exactly how a Feynman diagram works. And I can guarantee you Don Lincoln has no idea how that works. Because I asked Don to explain it to me, he just wouldn't speak to me. So maybe he does know how it works. But he's going to have to explain it to me because I don't think he does. He didn't understand anything else I showed you. And I think a 10-year-old, 12-year-old tops can see what I was showing. All right, I can feel I'm getting a little hostile, so I'm going to leave those clips in there because that's exactly how I feel from the gut. But I'm going to try to be pleasant. However, if we can get free energy using what I'm talking about, and this is the design here, and it's just almost nothing to do. I mean, literally nothing. If we can harvest that energy, which is these W and Z bosons, because we can separate, we can push one of them to one side and one of them to the other. You see the black and the red? That's what one of them is a black, one of them is a red. Now, we harvest one or the other, I don't care. But some way we can harvest one or the other. And I think we can harvest the white, glowy, pushy, burny one into a receiver, or either a heat receiver or maybe, because I imagine right at this exact spot, it must be absolutely incredible temperature right exactly at that one instant, because it's only for just an absolute instant and they come back together. So you might be able to see that with some kind of heat monitor. I don't know, but this is, like I say, if we could do this and carry things around in a pocketbook, I can't see any reason why we wouldn't want to do that. And I can't see any reason why Don is standing in the way of looking at this, which is what it is. He's standing in the way. He's not helping whatsoever. And If you want free energy, you're not going to get it from CERN or Fermilab. I can guarantee you that. And this is something, if it really works, and that's an if, that's a big if. I'm not saying it will. But to put in the kind of money they've put into this other stuff and having 50 years of absolute failure, and here I come showing exactly what they have seen, want to see, we can do, and not only can we do it, we can control it. It's not just an accidental splash of stuff everywhere. We can control it and squirt it to where we want to use it. This is really a disgrace to let this not be seen by top physicists, and I haven't had one of them respond to me. For whatever reason, you pick it. Now, once again, I do want to apologize, but I got to be honest with you. I was really upset with Don because he came out on one of his videos acting like a drunk robot. Oh, there's some guy out there who says he can see muons. I know who he was talking about. And I know that they know about me at Fermilab because one of the people from there told me that I've become a big joke there. And they had me on the big screen at their Christmas party or something. Everybody was having a big joke out of it. Well, that's fine. Hey, nobody will address it. Nobody will stick up for Don. Don won't stick up for himself. So, and I've been demeaned by all of them. Every single one. You should hear some of the things. Absolutely unbelievable. It's just shut up. Who the hell do you think you are? La, 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 la. Never one single word about what I'm wrong about. Never one question about how did this happen? How did that happen? None. Zero. So, again, this is going to be a book. Don's going to be highlighted. I'm sorry. It should have been addressed long ago. And it's going to be the shortest book I've ever written because it's going to be all backed up by actual evidence in videos and work done, experiments. Now, my claim is that hitting things head on like this and smashing things boom and finding debris all over, it means nothing. You're looking for the smallest bits that exist. They found them. They see them, the muon, electron, neutrino, because they keep seeing them over and over again, and there's nothing smaller, so they finally realize, yep, that's it. Well, they're all coming from things like this. And then one of these, which is one of those, it has both poles, can split and give us a stereo muon and an electron showers. I've shown it quite clearly. Now, let's continue on. And again, I don't mean to be harsh, but I feel this way. I can't help myself. After 7 years of denials of reality by the ones we trusted to get us free energy, the world is really in a trouble. I'm watching the weather patterns absolutely horrendous. And it's because as we burn things, the atmosphere is swelling. It's not that carbon can't get out, carbon won't let it get out, it's swelling, and we're scrubbing through particles that are in space, which are these particles, which are light particles, exactly like Don is going to explain, the quantum foam. It's out there. It's not just doing nothing. As we scrub through it, what do you think happens? Just think about it, for my God's sakes. Okay, my friends. Again, I don't mean to be so aggressive today, but I got to tell you something. I had 2 cups of coffee. I haven't been drinking coffee for years. I figured my wife got a new machine. I drank 2 cups of coffee. I'm off the walls. Anyway, here goes. This is 1940s. Once again, they're going into Feynman and so forth. Here it is.
The 1940s brought with them a fuller understanding of the quantum realm. Physicists Richard Feynman, Julian Schwinger, and Shinichiro Tominaga developed what we now call quantum electrodynamics, or QED. QED is not only a fully relativistic quantum theory, it also quantized the electric field. In much the same way that early quantum mechanics showed that matter came in discrete packets, QED showed that the electric field also came in packets that we now call photons. If you feel that quantum mechanics and relativity have made unsettling claims about reality, quantum mechanics will give you an ulcer. QED describes 2 electrons scattering from one another as one electron emitting a photon while the other absorbs it. That's not so hard to imagine.
That's exactly what does happen. A photon splits and then they come back together again.
However, the exchanged photons differ from the familiar massless photons of ordinary light.
No, wait, whoa. Oh, yeah, just massless photons of ordinary light. We just automatically know that. No, There's no massless anything, Don. Ordinary light is a particle, which I absolutely have shown, and if you have enough of those particles, it will add weight, and it does. Because if you heat something up with light, it will weigh more. Did you know that, Don? It will add weight. Just by heating something up with light, I don't care how you do it, but with light you can heat it up and it will add weight. So those are photons, and they have a weight. And plants eat photons. Ordinary light is not massless, Don. And there's no such thing as a massless, what do they call them, gauge bosons. Well, I can't say that. The glowy one might be massless, because as I see an atomic blast, the first things that hit the building is the white ones, and it just burns it up. And then, boom, the black ones come and knock it over. So it could be massless, but it's got a hell of a lot of energy. All right, so let's just get past the fact that light is massless. It is a mass particle. And that particle, like I said, is 0.000545 atomic mass units. If you took 1,836 or so of those electrons and added them together, it would weigh as much as one of your protons. And that's why when you smash things together, you're just seeing debris. It's actually meaningless, Don. Okay, he's not far when he's talking about this, but he is still wrong. Sorry, Don. QE describes two electrons scattering from one another as one electron emitting a photon. So they're scattering as one electron emitting a photon. No, the two of them back to back together, hold on, are the photon. Here's what you got, Don. And again, let's talk. I'm willing to talk. All right, you're saying that two electrons scattering from one another, these are electrons, and two of them together would be a photon. I can go along with that so far. Two of them scattering from one another as one electron. So each one of them comes apart, so you have two of these particles, but they're black and white, emitting a photon. No, it was the photon which emitted the electrons. You have it backwards, sir. I just noticed something. This was back from the mustache days. All right, listen. No. So he's saying two electrons scattering from one another, emitting a photon. Just exactly backwards. Okay, now here we go.
Scattering from one another as one electron emitting a photon while the other absorbs it. That's not so hard to imagine.
What happens is they emit a muon, an electron shower, and bring them back together as an electron. All right, so here it goes.
However, the exchanged photons differ from the familiar massless photons of ordinary.
Familiar massless? No, once again, wrong. Incorrectamundo. They are not massless, and neither are any of the gauge particles, except possibly the electron neutrino.
Light. For one thing, the photons of QED can actually have a large mass. This is not a problem in the quantum world, which is governed by, well, among other things, the Heisenberg uncertainty principle. Boiled down to its essence, this principle says that extra energy can simply just appear for a brief moment, as long as it disappears quickly.
It's exactly what I'm showing, Don. It's exactly what we're showing with the interaction here. It appears for a brief second because we're crushing, and it only stays to energetic like that for an instant, and it goes back together. So far, we're not that far off, my friend. And these are the particles that you have seen. I don't know why you won't accept them from me. We started with light, which was what CERN wanted to start with long ago, and didn't do it. We did it. All right, so here he is again. Can photons have mass? They absolutely have mass.
Boiled down to its essence, this principle says that extra energy can simply just appear for a brief moment, as long as it disappears quickly. The bigger amount of energy that appears, the shorter amount of time it can exist.
Well, I don't agree with that. The more energetic it is, the more it will exist. But it will still only exist for like an instant. And I can prove this. Let me show you that. I can prove it right now. All right, this is it. Obviously, it's existing longer in the green wavelength than it is in the red. This is going through the same slit at the same time. The slit is tall, and two round cylinders pinched together where the light, one is above and one's below. As it comes through, the red has no energy to speak of compared to the green, which is extremely energetic and lasts much longer than the red. So it's not, again, Don has it exactly opposite. So here's another shot. These are the same particles as the red, as the blue. And here they are, much more energetic, lasting much longer than the red. Okay, Don, I am sorry, brother. The bigger amount of energy that appears, the shorter amount of time it can exist. Once again, incorrectamundo.
Although the idea of massive photons already sounds pretty crazy,
No, it doesn't. If you just look at them, all you have to do is look, Don.
QED isn't done yet. If you follow that idea a little further, you'll find that QED predicts that nothing is really something. I'll wait while you process that last sentence. Nothing is really something. So let's see what that means. We'll start by taking this box, which is filled with air. The next step is to take all the air out of it and shield it so there are no external energy fields seeping into it.
Let me explain something, Don, which you don't understand. Everything there is coated with electrons. All of this stuff is coated with electrons. They're always on the outside, coating everything. What does an electron have? It has a negative charge. What does that do? It's a repulsive charge. So what happens inside there? There's going to be some molecular interaction between these charges. And anything that hits it from the outside is going to bounce those electrons around, and they will bounce on the inside. Let's see what he has to say. Energy fields, so you don't have anything coming into it. Let's see what he has to say.
Filled with air. The next step is to take all the air out of it and shield it so there are no external energy fields seeping into it. With nothing inside, surely it's empty, right? Well, let's start zooming in. Maestro, can you zoom a bit? Nope, not seeing anything. Maybe a little more? This isn't getting us anywhere. Time to pull out the big guns. Maestro, can you do the quantum zoom? The image you're seeing gives you an idea of the smallest quantum reality.
Exactly. There is particles everywhere that you cannot get away from them. Everything in between everything else is particles. Again, let me show you. All right, just stop for a second and think. Photons of light are coming through here. We call them photons because they're light. Well, what is a photon made of? I showed you what it's made of. It's made of that little four-way particle, two whites and two darks. And there's a bunch of them in there. There's not just one, I'm sure. But whatever is in front of it at that pulse, that magnetic wave which is in front of it, so it's a particle-wave duality, everybody else here is concussing. That's the only reason you're seeing all these little red particles. And what do those red particles represent? Those represent electrons in gases and extra charged particles, which we call heat. Heat is nothing more than additional charged particles in the air causing the glowiness that Don Lincoln is talking about inside that box. Now, if you took and went into absolute zero, you'd see nothing here. That wave would just go right through there because there would be absolute zero particles in front of it. Absolute zero means you've taken all of these heating particles out. And of course, you'd have to have it in a vacuum chamber. And then you bring it down to absolute zero. There's no energetic values to push back against. That would be a whole different story. And the more you reduce the heat in here, the less interactions you would see. The hotter it got, the more more glowy it would get pushing against this. I call it push to shove. The one that has the most energy is the pusher. The one that's shoving back is the shover. You don't push me, I'm going to shove you back. You say, yeah, like hell you are. I'm pushing, I'm tougher than you, and they always are. Well, not always. Sometimes things can be very strange. And in the Venturi is where the strangeness happens. Now I want to spend a minute on this one here because this is very important you understand. Remember I showed you all those little particles, all those little white particles that the wave had to crash through? Well, now look at them. They are glowing, just glowing like they're burning up. Why? Look at this. You see that wave there, those reverse waves? Let me see if I can home in on that a little bit. You see those reverse waves? That's called reverse EMF, reverse electromotive force. And what is causing that reverse force? You're not going to believe this, but this is true. This is a photonic bomb. I'm telling you right now. It's not an atomic bomb, it's a photonic bomb. It's subatomic down in the range of light. It's exactly what an atomic bomb does. It creates fission and fusion and extreme brilliance of energy and concussive waves, which are these reverse electromotive force waves. Look at the other light particles that are in the air. You never even know they were here. Nobody have an idea they're here, but beaten back against them, they glow like crazy. Look at this glow. There's an enormous amount of energy to be harvested here. And this right here, as I show in my little diagram, is the exact spot where they reform. And then they just grab onto each other. You see them all lining up to attach to each other? You see them? That's what they want to be attached. And that's what they do. And by the time they get out to here, they are Higgs fields. You want to see a splash? Where do you see this? These are going to be Higgs fields. I call it Higgs on steroids. Check this out. I call this Higgs on steroids. These are all Higgs fields. And what they are is when the white electron shower comes back together with the dark particle, they start to spin and create these fields. And every one of these little sprits is going to create another one of these fields. I mean, they're everywhere. I got other shots. Hold on. All right, these are Higgs fields. This right here is coming straight at us, like this, coming straight out this way. So what is happening between here and these? All you have is white sprits. Can you see these little tiny see it? These little sizzles? Well, all of those want to be away from each other. Way back here, they're starting to recombine way on the edges because they can jump in. That's all they want to do is jump back in, the black ones. And this is where they jump in. Now, this one here, that is the crazy one. Hold on. Well, let me just explain to you why I say it's crazy. We're all looking at fields that are circular and have dots all around them. Well, why? I will show you why in a second. But this one doesn't. That's a white spot. And you can see it's got a trail right behind it. So it's coming out with these. It was a spritz at one time, but it's going left instead of right. And it's harvesting energy onto itself. And here's what happened. This one here hit one of these fields and turned into a, I don't know what, but it turned into this right there. These are the Higgs fields. That's well known now. There's no mystery about that. This is a mystery. That, I have no idea what it is, but it appears to have had a form and an interaction with another field's field. You feel me? Here it goes. What it is, je ne sais pas. You see that? This is the tip coming at us. These are the wells around the tip. These are the particles spinning like crazy and concussing ahead. And it looks to me like the black and the white, for some reason, are split apart here, but not down here. Every now and then you'll find them crushed or something, whatever causes them to separate and show the black and the white separate like that, as like an eggshell. I really haven't fully understood that yet. But I know that this is the particle coming at us, and we're seeing the bump. Let me show you a different way. All right, hopefully this will have a little better impact. This are these circular patterns, and they have a center core to them. Every one of them has a center, which is it has to be banging other electrons out of its way as it's coming forward. Get out of the way, get out of the way, get out of the way. And so they push them into the center, and they keep banging and banging and banging and banging, and they keep pushing. It's push to shove, push to shove, push. It's an elegant pattern. I mean, look at it. It's just amazingly elegant. So I don't know if I'm right or not, but I think I am. And I can tell you one thing for a fact. The light is coming out of here, and these sprits, I think this was one of the ones that caused all kinds of havoc, and you could see that Higgs on steroids, something like that. And then you see these kind of things. But these are Higgs fields, and they show up at a certain distance. Again, that distance is right here, right there. So here's what a concussion is. The Venturi brings everything together, explosion, a photonic boom. Out the other side squirts raw energy, supposedly trillion electron volts, where it started off with, let's say, 1,000,000. A trillion, that's a pretty good increase. If you could harvest that in any sort of a percentage, you got free energy. And this we did for almost nothing. So just think what the Department of Energy should be able to do with their resources. That's all I'm asking for, is to check it, to see what they can do. No big commitments. I'm not asking for any big programs. I'm asking for just see if my stuff is right. If it is, let's make some free energy. Let's get ourselves out of this problem we're having with the whole rest of the world. All right, this is a light wave proceeding down this way. Light spins, so that's why you see some going that way, some of them going this way. I can prove that spins. Now, why are we seeing a heavier glow here? That's because they're interacting with each other's fields. Push to shove. Out here, there's very little interaction. There's a lot less energy, a lot less glow. Anytime you have a lot of glow, you have a lot of energy. Anytime you have a lot of push, you have a, and somebody's shoving back, you're going to get that glow. And you see how fast these puppies are spinning? I mean, they are just zip. I don't know if I showed you this or not, but before we go too much further, we're going to start talking about fields in space. Because all these fields have interactions with light coming at us from distant sources. So the Hubble telescope is it's just not going to work for distance. There's too much interaction between particles in the quantum foam. We're going to go back again and have Don explain that. But how could you possibly think the Hubble telescope is not going to be interacted by these things in dust and magnetic fields and light particles and the quantum foam? There's just too much dogma that can't get cut through and keep your job. And that's all I can think, because nobody can miss this. You just can't miss it. And to dismiss me as a tinfoil hat guy, I was not very, very happy about that. As I said, this is going to be the part to the book that is going to be literally the book. It's going to be called the shortest book ever written about physics. And it will be, because it's only a couple pages. I can do everything. There's very, very, very few simple, tiny little things that make up everything. And then how do they interact? Now, that's a whole different story. Because then you get into molecular configurations, nucleophilic substitution, the arrangements of electrons around the nucleus and all of that. And it's all vibration. Tesla was correct. Its energy is based on vibration and frequency. And now Don Lincoln should understand about frequency creating more and more complex structures. The lower frequencies are down in the hydrogen, helium, lithium, all in there. But you get up into the really, they're just humming together, but staying together loosely. Now, I would like to invite Don Lincoln or any other physicist, anybody, to interact with me on this book, because like I say, I want some debate. I want somebody to say, oh no, Roger's crazy because of this, this, or this. However, I would request you to refer to what I am saying, not just because what you said and what you read. I want you to say, Roger's wrong, at 10:25 he said da-da-da-da-da, and here's my statements. That's what I want. And I want the same thing from Don Lincoln, because it's going to be kind of scathing. And it should be, because I want some interaction. All right, so let's get ready to start over. Just watch this. This is by Latham's Crazy Machines. They got a brass ring, and they're going to put negatives surrounding a positive core. That's the dipole electron flood theory. That's what molecules and atoms will be made of. Now, they will not be even. So this particle wants to get in to that black. Well, it's already got enough white ones around it to say, no, you can't get in here, but you can stay right there. This is what quantum's all about with a tractor beam toy. There it is, Don. It's not a virtual particle. It's a particle stuck at a distance because its negative wants to get to this massive positive. The black ones appear to be extremely aggressively attractive. So they get coated with the negatives, and then another negative says, oh, I want to get right up close to that one. It says, no, 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 you have to stay out there. That's quantum. Okay, those aren't virtual particles. Those are virtual fields. They're fields, they're not virtual. Now we got another issue there, Don, my friend. Not vertical particles, they are particles.
There is another measurement that supports the virtual particle idea. This has to do with the strength of the magnet formed by individual electrons. Electrons have electric charge, and they also act as if they spin. Just as in the classical world, a rotating charged object becomes a magnet. And because we...
All right, rotating particles like the body of the sun, the sun, the earth, all bodies spinning through particles in space, which are negative particles. You got to be spinning through negative particles. That's what a motor is. Here, hold on a second. All right, here's what a motor is. Inside this motor, there's an armature, which is this particle, and then outside the armature is a field, which is all the electrons. You see the field? Pull this in. When I'm spinning through that field, I got to push this glob of electrons through that magnetic field. So it forces electrons out these conductors. However, that's if I was spinning it myself. If I put electricity into this, it does just the opposite. It makes the motor run. You can feel it. If you spin a little DC motor, you feel it. Click, 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 click. That's making and breaking through the magnetic field. So what he's saying is correct. And he's talking about, we know the electrons charge and spin. Well, no, Don, I don't think you do, my friend. An electron is not a plus, it is a dipole. Electrons have electric charge, and they also act as if they spin. Well, yes, I can agree with all that.
Just as in the classical world, a rotating charged object becomes a magnet. And because we know the electron's charge and spin, we can predict the strength of the magnet each electron should be. When the prediction and measured strength of the magnet formed by an electron were compared, there was a tiny discrepancy. They disagreed by 0.1%, 1 part in 1,000. A small effect to be sure, but a disagreement nonetheless. However, when the simple calculation was replaced by one using quantum electrodynamics and virtual particles, the agreement between data and theory was restored, and the restoration was better than anyone dreamed.
You see these magnetic strength of an electron? What is he talking about here? Predicted what? Measured what? Well, I can tell you one thing. These are masses, appears to me. because he's showing 100,115. That's exactly 2 electrons added together to a proton. All right, which would be probably helium. I don't know what they're looking for. He's saying what they, he's very vague on what any of this stuff means.
The two numbers now agreed to 12 digits.
About what?
This is the most accurate measurement mankind has ever made. This incredible level of agreement is believed.
The magnetic strength. Well, how do they know what they're talking about, magnetic strength? What's this number represent on? That's what we need to interact about. Just throwing out these numbers, no, it absolutely defines this and that. I don't even know what you're talking about.
Definitive evidence of the existence of the quantum foam.
The quantum foam's there. And this may be what he's talking about. He's finding particles all over the place. Instead of just one proton, he's finding these electrons floating around, because that's the weight of 2 electrons. An electron weighs 0.000545. So if you add 545 twice, you get 10, 11, really. So it's 1.011 and 5. I think it's almost exactly what I'm talking about. Very confusing, though. So let's let him go on.
Now, let me whet your appetite for something interesting. When we make a similar measurement of the magnetic strength of the muon, which is a cousin of the electron, the agreement is still good. It goes out to 8 places. But a disagreement appears in the 9th digit. While this discrepancy could be because of a faulty calculation or measurement, scientists are pretty confident that the disagreement is real. It could be the first sign that our theories are breaking down. Scientists are so intrigued that they've embarked on a new experimental program to better measure the magnetic strength of the muon. The G-2 experiment studied the muon for many years at the Brookhaven National Laboratory.
I want to tell you something. I had an interaction with, it's Jefferson Laboratories. I mean, they got so many of these things going on. But I've never had anybody interact, and the guy from Jefferson was absolutely unbelievable. They all are. Nobody's interested in talking other than making these gigantic experiments, and I think it's got a lot to do with funding, and, they can't be wrong.
Limitations in the existing accelerator complex led scientists to move portions of the accelerator and detector to Fermilab, which has the ability to make more muons and thereby study this phenomena more.
I can make muons coming out of your ears, Don. You just ask, my friend, and I will supply them all over you.
Precisely. The G-2 experiment is expected to begin operations in 2016 or so. We scientists are incredibly interested in the outcome of this experiment, as it may lead to a new and better understanding of the universe. However, even with this exciting discrepancy, we must not lose sight of the fact that the agreement between the predicted and measured strength of these subatomic magnets is spectacularly good. This agreement, combined with the observed Casimir effect, gives incredible confidence in the quantum foam. And the idea of the quantum foam leads to an entirely new paradigm, a completely different way of thinking about space. Empty space isn't empty. It's a bubbling, writhing, frantic place with energy converting to matter and back to energy again.
Which interferes with particles that are coming at us. And if you look at the arms of the galaxy, there are hot spots and then there's cold spots. Depends on where you're coming through. Where is that light coming through? Is it coming through a lot of density? Is it coming through a lot of non-density? Galaxies are not homogeneous. And so Hubble is really kind of silly to think that that's going to measure where things are in space.
Now, I understand that this claim sounds hard to believe, but this new view of the subatomic world is real, and scientists can prove it.
I have done.
You may never look at foam the same way again.
You may never look at Don the same way again. I'm sorry, Don. All I want to do is talk, my friend. And I'm still totally open to that. But I have no other way to respond. So we're just going to keep doing this. And I've been doing this now for, it's got to be a couple of years now. because you're the guy. You're the guy in control. So until somebody stands up for you, you stand up for yourself. I see no scientific acumen here, my friend. I still love you.